There is a device with no moving parts, no fuel of its own, and no battery. You bolt it to a hot surface, and it produces electricity. The heat is already there. The device just catches what was being thrown away. China understood this before most of the world, and right now, in 2026, China is the largest single producer and researcher of these devices on the planet, while the rest of the world is still debating whether they are worth it. This is the story of the thermoelectric generator, a 200-year-old principle that China turned into an industrial strategy, and the uncomfortable reason it never became the technology it should be. The physics behind it is almost offensively simple. In 1821, a German Baltic physicist named Thomas Johann Seebeck took two different metal wires, joined them into a loop, and heated one of the junctions. A nearby compass needle moved. He thought he had found a new form of magnetism. He had not. What he had actually found was that a temperature difference between two joined conductors creates a voltage. No battery, no chemical reaction, no moving parts. Just heat on one side, cold on the other, and electricity flowing through the middle. That is the Seebeck effect. The first documented proof that thermal energy can convert directly into electricity using nothing but solid materials. For a century, the discovery sat in university laboratories, useful mainly for measuring temperature in industrial thermometers. The voltage produced by ordinary metal junctions was too small to power anything meaningful. To make it useful, someone needed a better material, a far better one. That someone came from the Soviet Union. A physicist named Abram Yoffe spent the 1920s and 1930s at a laboratory in Leningrad working on semiconductors. He demonstrated that certain semiconductor compounds could produce thermoelectric voltages orders of magnitude larger than ordinary metal pairs. His foundational work, published in 1929, became the theoretical bedrock for every practical thermoelectric device that followed. Then came 1942 and the German invasion, and theory became urgency. Yoffe and his colleague Yuri Maslakovets built a battlefield generator called the TG-1, known among Soviet partisans as the Partisansky Kotelok, which translates roughly as the partisan cooking pot. It looked like a metal kettle. Partisans filled it with water, placed it on a fire, and the temperature difference between the hot bottom and the water-cooled interior drove semiconductor elements that produced 10 watts of continuous electricity. Enough to charge the batteries of a field radio behind enemy lines. No fuel depot required. The fire was already burning for warmth. After the war, Soviet engineers refined the concept for civilian use. They built a compact generator designed to sit on top of a standard kerosene lamp, a device called the TGK-3. The flame heated a faceted metal core to roughly 300 degrees Celsius. Aluminum fins on the outside, exposed to open air, stayed near 30 degrees. Between those two surfaces sat semiconductor elements made of paired p-type and n-type materials. A temperature gradient of 270 degrees drove electrons from the hot side to the cold side, and that electron migration was a current. Continuous, free electricity from a lamp that was already burning for light. The Soviet government manufactured millions of these units and distributed them to rural households beyond the reach of the electrical grid. For those families, 2 or 3 watts of free electricity was not modest. It was the difference between hearing the outside world on a radio and not hearing it at all. The physics has not changed. What changed is who decided to act on it at scale. Pause for a moment on how strange the physics actually is. There is no combustion happening inside the device. No turbine, no fluid loop, no membrane under pressure. You take two semiconductor materials with opposite charge carriers, join them at their ends, heat one junction, and keep the other cool, and charge carriers migrate from hot to cold the same way water flows downhill. That migration is a current. The device simply sits there, motionless, converting a temperature difference into voltage, year after year, with nothing to service and nothing to replace. The most spectacular proof of this reliability is currently 15 billion miles from Earth. NASA launched Voyager 1-inch 1977 with 3 thermoelectric generators powered by radioactive decay instead of a flame, but running on the exact same Seebeck effect. At launch, they produced a combined 470 watts. Nearly 5 decades later, still operating, still transmitting data from interstellar space, they output around 220 watts. No maintenance crew has ever touched them. No fuel has been added. A temperature difference, and nothing else, has kept humanity's farthest-reaching machine alive for almost half a century. Back on Earth, the numbers that matter are less poetic, but more immediately important. More than 72% of all primary energy that human civilization produces is ultimately lost as waste heat. That is not a rounding error. That is the dominant outcome of burning fuel. Every car engine, every industrial furnace, every power plant, every steel mill discards most of what it consumed as hot exhaust gas, heated water, and radiated surface warmth. The United States Department of Energy estimates that between 20 and 50% of all industrial energy consumed in the country escapes as waste heat through exhaust gases, cooling water, and surface radiation. Globally, the figure is comparable. According to industry statistics, low-temperature waste heat below 300 degrees Celsius accounts for more than 89% of industrial waste heat. And thermoelectric generators are particularly well-suited to exactly that temperature range. Not the extreme high-temperature environments that require exotic engineering, but the mundane, continuous, enormous flow of moderately hot surfaces that industry produces every single day. Projections in the World Energy Outlook 2024 report highlight the potential for recovering waste heat at temperatures below 100 degrees Celsius, which accounts for approximately 70% of global waste heat. That is the opportunity, and China saw it. China accounted for nearly 34% of global thermoelectric materials production in 2023. That single figure tells you something important about where the center of gravity of this technology has moved. Publications in thermoelectric research are mainly contributed by Asian countries, with the most coming from China, followed by the United States, South Korea, Japan, and India. China is not just manufacturing these devices. It is the dominant country in the academic literature that is advancing them. China dominates the global thermoelectric modules market with a 22.3% share, driven by research and development, investment, and strong industry infrastructure. To put that in perspective, the next closest national competitor in the same market sits roughly a third of that figure. One country, nearly a quarter of all global thermoelectric module production and consumption. In 2023, China announced over 15 pilot projects deploying thermoelectric generators at large-scale industrial plants, targeting a cumulative annual waste heat recovery of 4.2 terawatt-hours. For reference, 4.2 terawatt-hours is enough electricity to power a mid-sized European nation for several weeks. Large-scale demonstration projects in cities like Shanghai and Shenzhen showed widespread thermoelectric generator adoption in factories and power plants, which collectively reduced annual carbon dioxide emissions by over 200,000 tons in 2024. China aims to achieve the peak of carbon dioxide emissions in 2030 and become carbon neutral before 2060, known as the dual carbon policy, to tackle climate change. That policy is not just an environmental pledge. It is a national economic directive that makes waste heat recovery financially rational in a way that previous regulatory frameworks never did. The China Carbon Emission Trade Exchange brings huge economic benefits to companies in low-carbon industries, and companies seeking to become carbon neutral must reduce their own emissions rather than simply pay for reductions elsewhere. That creates a direct financial incentive to bolt a thermoelectric generator onto a furnace exhaust pipe. In China, energy-intensive industries dominate the industrial sector and have significant potential for waste heat recovery. Steel, cement, chemicals, ceramics. These are industries where the heat being thrown away is not incidental. It is enormous, continuous, and currently generating zero return. At a flow rate of about 3 cubic meters per hour, a thermoelectric unit, with a volume of about 3 cubic meters, can generate a power of 15 kilowatts at a temperature difference of 60 degrees Celsius. 60 degrees of temperature difference. The exhaust pipe on a diesel generator runs hundreds of degrees hotter than that. The surface of a cement kiln runs more than 1,000 degrees hotter. The scale of the untapped resource is staggering. The global industrial sector spent over $600 million on thermoelectric waste heat recovery solutions in 2023, with China and Germany leading pilot deployments at cement and steel plants. Then there is the supercritical carbon dioxide story, which is where China just did something genuinely unprecedented. The world's first commercial supercritical carbon dioxide power generator started operations in southwest China's Guizhou province recently, a significant milestone in the global transition toward high-efficiency waste heat recovery. Known as Khotan-1, the generator uses carbon dioxide instead of steam to transfer heat, and each unit of the project boasts a power generation capacity of 15 megawatts. This is the same underlying principle, converting thermal energy into electricity, scaled from the kerosene lamp of the Soviet partisan to a 15-megawatt industrial power station. The physics, Seebeck, discovered in 1821, is now generating commercial-scale electricity in Guizhou in 2025. Industry experts believe the innovative thermoelectric conversion technology comes at a critical juncture for China's energy landscape, as the country's electricity consumption is expected to reach a record high in 2025, with total power use projected to surpass 10 trillion kilowatt-hours nationwide. 10 trillion kilowatt-hours. China needs every watt it can find, and it is increasingly finding them in the heat that industry was already producing and discarding. Here is the honest friction in this story. The efficiency numbers on thermoelectric generators are not impressive by the standards of primary power generation. Commercial modules in 2026 operate at roughly 5 to 6% conversion efficiency. Thermoelectric modules are not as efficient as other energy conversion technologies. And despite ongoing improvements, the efficiency rates of existing modules typically fall between 5 and 10%, which, in certain applications, cannot be competitive enough when compared to alternative solutions. That criticism is real, but it is also slightly dishonest because it asks the wrong question. 5% of energy that was going to be thrown away is not a loss compared to 20% of a solar panel. It is found money compared to zero. The waste heat exists whether or not you capture it. The furnace is running. The exhaust pipe is hot. The question is not how efficient the generator is relative to a coal plant. The question is how much of the energy you were already paying for and then discarding you want to recover. Researchers at Pennsylvania State University demonstrated a thermoelectric device in 2023 that reached a conversion efficiency of 15.2%, the highest ever recorded for this technology. Commercial modules are improving. Earlier research demonstrated modules with an outstanding conversion efficiency of 8%, which is 40% higher compared to state-of-the-art commercial modules available at the time. The performance gap between the laboratory and the factory floor is closing. So, why is it not everywhere? The Soviet answer was straightforward. The electrical grid arrived, and 2 watts from a lamp-top generator could not compete with 20 amps from a state-subsidized power line. The modern answer is more structural and, frankly, more frustrating. The entire energy economy of the industrialized world was built around centralized generation. A fuel burns somewhere far from you. Electricity travels through wires to your building. A utility charges for every kilowatt hour that crosses its meter. That system works. It also creates a financial architecture that has no mechanism for capturing the value of what happens at the other end of those wires, where energy arrives, gets used, and its waste heat disappears into the air. A thermoelectric generator bolted to an industrial exhaust pipe produces electricity that never passes through a utility meter. It has no room in the standard energy audit. It does not qualify for the standard incentive programs in most Western countries. There is no federal tax credit for it in the United States. There is no standardized installation certification. It is not prohibited. It is simply invisible to the system that decides where investment goes. In China, the regulatory structure is different. State ownership of major industries, centralized carbon accounting, and a national mandate to hit dual carbon targets by specific dates create conditions where the national interest and the industrial incentive point in the same direction. When the government says waste heat recovery matters for the carbon target, factory managers have both the regulatory obligation and the financial mechanism through the carbon trading exchange to act on it. China invested 30 million Chinese yuan to develop thermoelectric materials as part of a coordinated national research effort that also includes university research programs, industrial pilots, and manufacturing scale-up, all moving in the same direction at the same time. That is the structural difference. Not that the physics works better in Shenzhen than in Ohio. It does not. The electron migration is identical on both sides of the Pacific. The difference is that one system has decided this technology matters for reasons beyond individual quarterly returns, and the other has not yet made that decision. The global thermoelectric modules market reached a value of nearly $884 million in 2025 and is expected to grow at roughly 9% annually during the coming decade, potentially reaching over $2 billion by 2035. That growth is largely being pulled by industrial waste heat recovery, automotive exhaust recovery, and the expansion of off-grid power applications in regions where the electrical grid has not reached or is unreliable. In February 2025, Ferrotec Corporation announced the expansion of its production capacity in China for high-efficiency thermoelectric modules, aiming to meet growing demand from electric vehicle battery manufacturers and laboratory instrumentation providers. Ferrotec is a Japanese company expanding its production inside China because that is where the manufacturing infrastructure, the material supply chains, and the demand growth are concentrated. Think about what that means for the supply chain of any future thermoelectric build-out outside China. The raw materials, the manufacturing scale, the institutional knowledge, and the research pipeline are predominantly located in one country. China accounts for nearly 34% of global thermoelectric materials production, and China is the global powerhouse for thermoelectric material manufacturing and usage, supported by its mature electronics sector, robust energy-saving initiatives, and booming electric vehicle and smart grid segments. Any Western industrial push to deploy this technology at scale would largely depend on a supply chain that runs through China. This is a pattern that should by now be familiar to anyone watching advanced energy manufacturing. Solar panels, electric vehicle batteries, rare earth magnets. The technology was often invented elsewhere. The manufacturing advantage was built systematically through patient state-backed investment, low production costs, and a domestic market large enough to create economies of scale before the global market was ready to absorb the product. The thermoelectric generator follows the same trajectory. The physics is 2 centuries old. The Soviet Union validated the engineering at scale. China has spent the last 2 decades building the industrial base to manufacture these devices cheaply and deploy them broadly. The dual carbon policy created the national demand. The carbon trading exchange created the financial return. The rest of the world is now looking at a technology it largely ignored and wondering how to build an industry in it that China already built. There is something almost elegiac about the original Soviet TGK-3, a device the size of a bedside lamp, sitting on top of a kerosene flame in a Siberian farmhouse, producing enough electricity to run a radio. No installer required, no grid connection, no monthly bill, just a temperature difference, and solid-state physics doing what solid-state physics does. The families who received those devices did not know they were using the same principle that would one day power a spacecraft past the edge of the solar system or generate 15 megawatts from a carbon dioxide turbine in Guizhou. They just knew the radio worked. The principle is still the same. The heat is still there. More of it than ever, pouring out of every industrial process, every vehicle engine, every data center cooling system on Earth. The only variable that ever changed was whether anyone decided it was worth catching. China decided. That decision is now embedded in factories, research programs, carbon markets, and manufacturing capacity. Whether the rest of the world makes the same decision, and on what timeline, is the question that will shape a significant portion of global energy efficiency over the next 20 years. How much waste heat do you think is escaping from the places around you right now, and does it frustrate you that almost none of it becomes electricity? Leave your answer below, and if you want to keep following how China is reshaping the global energy and technology landscape, subscribing means you will not miss what comes next.